Okay, thank you everybody for coming. My name is Keaton Strongman, and today I'm going to talk about a kind of older concept. And this is the idea of central volcanic complexes in the Abitibi. And we're going to see if we can't resurrect this concept a little bit and apply it to look at some origins and some potential modern seafloor analogs to compare with. So the central goal of my project is to examine the volcanic and subvolcanic architecture of the Abitibi with the specific goal of comparing and contrasting with modern seafloor settings. And we're particularly interested in seafloor settings, like you can see on the right here, from the northeastern Lao that have a microplate-like configuration, because we think these might be some of the best analogs for Archean greenstone belts. So how do you do this? How do you go about comparing rocks that are 2,700 million years old to rocks that are only a couple million years old? Well, one of the things you can do is you can work with unified data sets. And for this, we can turn to geophysics. So Aaron showed this model earlier. This is a MOHO depth model throughout the Abitibi. So it's effectively a model of crustal thickness, with thicker crust in red and orange and thinner crust in blue. And we go from a thickness of about 45 kilometers in the thickest portion to a thickness of about 32 kilometers in the thinnest portion. So that's over 10 kilometers of thinning in some parts of the Abitibi. And what you can see here are a series of negative anomalies, thinned and attenuated crust. And these don't just occur as dots, they seem to occur as linear anomalies that form a kind of network. And you can imagine that this might be a rift network. And the reason we think that this might be the case is this is exactly the kind of pattern that you see underneath extensional zones within areas like the Lao. And potentially, these might be rifts or spreading centers that would bound things like microplates. And this is great, but it's working with the base of the crust, right? 45 to 32 kilometers. And we really want to know what's going on the surface and make comparisons with the surface. And so for this, we need maps. And this is really where the work that Metal Oceans has done has been instrumental in allowing us to finally compare at the same scales. Because before we had maps like the one on the ground next to me here, which is a compilation of basically all of the mapping in the Southwest Pacific that we've done, we were working with maps of the entire ocean that were mapped by age, or with maps of individual sulfide mounds that were done from ROV dives. So now we're working with things at the same scale. This is an example of one of these maps. This is at a more detailed scale here of an area called the Mangatulu Triple Junction. And it's highlighted beautifully here by the orange, which shows this nice Y shape marking out the intersection point between the three arms of rifting. But you don't need to worry about all this text here, but I wanted to just highlight this orange unit here because it's important to look at what is being mapped. So first of all, the title of this unit is Axial Back Arc Volcanic Ridge, okay? It's also noted here that it's part of the upper unit of the back arc assemblages. And if you read out the actual description, it's volcanic ridge marking the active spreading center, commonly with discrete volcanic edifices, and specifically things like cones and domes, dike complexes, or calderas. So what's being mapped here? Well, we're mapping effectively three separate things. We're mapping crustal type, first of all, and we could do this. It's a bit of a luxury because we're in the modern setting, so we know if it's an arc or a back arc or oceanic plateau. We're also mapping by age. This is upper, and the next unit is middle and lower. Now, this isn't vertical stratigraphy. We're looking at distance from the rift. Further from the rift is older, closer is younger. So we're mapping by age as well as crustal type. And finally, volcanic ridge. We're mapping volcanic landforms. That's what's actually being drawn on these maps. And this is where we run into some challenges, because volcanic rocks, like we have mapped in the Abitibi, are non-unique to their landforms. A good example is pillared mafic flows that can occur in a whole variety of settings. They're not diagnostic of a particular volcanic landform like a stratovolcano or a comb or dome. So this is what really brings us to this central volcanic complex concept, because this was one of the first attempts to actually work out geographic volcanic complexes and potential volcanic landforms on the seafloor, or in the Abitibi. And this is an example from Goodwin and Riddler in the 70s, and their definition was a semi-independent ellipsoidal volcanosedimentary domain. It's a bit of a word sandwich, but effectively what they're saying here is they're trying to find volcanic landforms. And you can see they've marked a series of these out throughout the Abitibi here. And what you'll note inside here are a series of dashed symbols. These are felsic volcanic rocks. So they're recognizing when they make these that they're not looking at an individual volcano most of the time with a single eruptive center. They're looking at a series of eruptive centers and cogenetic formations to trying to put them into a larger landform. But there are some challenges with this. And the real issue comes from all of the modern high-precision geochronology that's come out since the idea was introduced. And now we know that a lot of these boundaries don't really make sense. So this is a chronostratigraphic map of the Abitibi. So the younger colors are red and orange, and the older colors are blue and purple. What you can see is the nice age progression through the Abitibi that Aaron was showing earlier, from older material in the north down through the east into material that's younger. But what you'll note is these central volcanic complexes from Goodwin and Riddler cross across multiple boundaries and often include units of very disparate ages, particularly in the southwest here, where we have Deloro ages 2735 in contact with things like Blake River that are much younger. So we have to modify the definition a little bit in order to use this. And by a little bit, I mean we added one compound word here, a multi-stage semi-independent ellipsoidal volcanosedimentary domain. And this is important because it represents a shift in how you would think about these. You're not looking at a single static landform, you're looking at a cumulative product of growth over time, a landform that's modified over time in multiple stages of growth. So this new definition allows us to include all of the products of the edifice construction and modification, along with synvolcanic intrusive rocks, things like dikes and sills that record inflation of the edifice, and sometimes, but not always, central synvolcanic plutons that may mark volcanic necks and corridors through which magmas are traveling. So what are we looking at now? Well, we're looking at potentially single large volcanoes, but probably more often we're looking at coalesced composite edifices. In other words, multiple volcanoes that are growing at the same time and at different points in time that are overlapping onto one another. So what I've done is I've taken this criteria, and we've gone through looking at all of the newer mapping and geochronology and tried to break out geographically isolated complexes using the formation mapping through the Abitibi and parts of Ontario. And I put them on top of Taus's compilation assemblage map here, and you'll see that they're colored based on their stages, with starting at 1 for every single complex. And I've used the age boundaries from the assemblages to subdivide the various units out. So I've just reorganized them here so they're a little bit easier to see and distinguish from one another. And the first thing I want you to pick out from this, without looking too much at the patterns, is that the scale of these features is consistent now with modern seafloor features. So you notice this is 40 kilometers. It's exactly the same width as these black bars. So these are all at the same scale, all of these maps. And we can see a number of seafloor features here, including Peggy Ridge, the Mangatulu Triple Junction, the Lao Eastern Transform Zone, the Rochambeau Rifts, and the Northwest Lao Spreading Center. So we're dealing now with things that are finally at the same scale, and finally we're comparing maybe not apples to apples, but certainly not apples to oranges anymore. We can also pick out some just basic observations about the patterns of these complexes. The first thing is that we have multiple morphological subtypes. The first example here are concentric domes. These are areas where we have rocks of a certain age that are surrounded almost entirely by rocks of a different age. There are two really good examples of these. Jetel Estrades here, which has older material in the core with progressively younger material outwards, and then Kidd Kamoskosia, which has the opposite pattern, younger material in the core and older material outboard. Now at Jetel Estrades, we're probably looking at a dome pattern here that's generated mostly by deformation. But at Kidd Kamoskosia here, this younger material is Blake River age, and the older material is Kidd Monroe age. So we're missing the Tisdale here. So this is not likely just a structural pattern. We're probably looking at younger volcanic material that's actually punching through older volcanic material. The second type are elongate zoned, and these are where one side of the complex represents one stage of growth and the other side of the complex represents the other. Now, these areas here, Valdor and Amos, are both heavily deformed, so there's some question as to whether or not this pattern is entirely structural or perhaps has some volcanic inheritance to it. The final type are multi-part complexes, where we think we can break out discrete volcanic centers and different, potentially, volcanoes that comprise a larger complex. This is Kevelaw and Langlaw here, and you can see we have an older pulse of volcanism that gets progressively younger as we move to the south, but this pulse down here is completely isolated from this one up here. So the next thing that we can look at is we can bring that crustal thickness map back up, because it's important to understand where we might be. If those are rifts, where are these complexes sitting? We can see that there are a number of complexes, like Chibougamau, for example, that sit directly on thinned crust. There are others, like Jetel here, which sits on thickened crust, and then there are some, like Amos and Beirut, that share thick and thin crust. But one thing I want you to note here are the VMS deposits, which are plotted in red dots. The VMS occur in the thinned crust. That makes a lot of sense. But even within a given complex, look at Amos here. Thick crust in the northwest, thin crust in the southwest and in the east, and that's where all the VMS are. So crustal thickness is controlling VMS even at this scale within the complexes themselves. The next thing I want you to think about for VMS is that these effectively represent the VMS camps. Matagami, Chibougamau, Amos, Valdor, Noranda, we're effectively separating out VMS camps here. And within the VMS camps, the metal associations and mineralization styles are mostly consistent. There's some obvious exceptions to this. Bousquet-Laurent is very different from the main camp deposits in Noranda, but generally this pattern holds up. So we're looking at some feature that potentially is also controlling the overall style of the VMS. So if we really want to get into this, we have to get into the actual complexes and pull them apart. So we're going to look at two examples here, Chibougamau and Kevelaw. So Chibougamau is one of my favorite areas in the Abitibi. It's extremely, extremely interesting and very unique, in particular in its mineralization styles. It's located, you can see here, in the top northeastern corner of the Abitibi, just in this little red outline here. And it's elongate zoned. We have one side that's predominantly one age and the other side that's predominantly the other age. It's located directly on top of some of the thinnest crust in Chris's model. And the mineralization styles here are really interesting. Instead of being dominated by hydrothermal systems and orogenic systems like we are in most of the other parts of the Abitibi, here we have magmatic hydrothermal systems, as well as traditional VMS. And these are represented by some of the main camp deposits in Chibougamau itself, which are very strange and have kind of a controversial origin. But there's also true epithermal-looking deposits like Eagle, Telbay, Brosman, and Berrigan that have atypical characteristics that might fall into an epithermal class. And finally, there's synvolcanic intrusion-related gold-copper deposits here that resemble porphyry settings in the Lac Doré complex here in the south. So we have a really nice mixture here of mineralization styles. Volcanism in this complex is encompassed by the Roy group. We have two main cycles that we're dealing with here that occur over about 14 million years. So that's quite a long time span, particularly when we consider features on the seafloor. The entire Lau opened in less time than that. So there are some issues when we're comparing through time. So let's take a look at the stratigraphy. I'll try not to put everybody to sleep here after lunch with stratigraphy, but we'll take a quick look. The cycle of Chibougamau is two cycles. The first cycle here is Deloro in age, and it begins with the Obotogamau and Wakanichi formations. These are both predominantly mafic, pillowed and massive mafic flows with minor interbeds of argillites and tuffs, but near the top of the Wakanichi, we have a series of discontinuous felsic centers. Now these formations are both represented by this dark green here, and you'll note that there's no rhyolites on this map, and that's just a product of the scale. They do occur, but they're quite small, and one of them is underneath this dot here, which is Lemoyne, and there are some over here in the west. But this is important because this is isolated from the rest of the package. So are we looking here at multiple eruptive centers? Probably. So what are we actually building? Well, this series is filled with mafic dikes and sills. It's been injected extensively. So potentially we're actually building a constructive edifice here, but that's not especially clear. Potentially we could be looking at shield-style volcanism. Now, the second cycle is really where everything starts to get interesting. There's a small time gap between the two, and then we're into the Bruno and Blondo formations. Now, the Bruno formation is pillowed mafic flows that transition upwards into andesites, and then we have a mixture of volcaniclastic material and argillaceous units. The Blondo formation is really interesting. Here we have argillites interbedded with scoriaceous felsic volcanic rocks. And the scoria here is really important because scoria doesn't float. Pumice, when it erupts, can float and distribute itself all over the planet, but scoria tends to occur pretty close to eruptive sites, and it requires magmatic degassing, so we're not in a deep water setting. You can also see that in this top of this formation here, we have things noted like cross-bedding. So potentially we're in a shallowing sequence here that is maybe even shoaling and emergent in nature. But a lot of people will wonder, well, how do you know that's not just porcupine-age sediments, and that's just what we're looking at here? Well, we know that because of this series of sills here called the Cumming sills. These are mafic to ultramafic sills. They're only represented by one here in the actual map because of the scale of the compilation, but you can see that there are actually three that mark out this boundary, and these are ultramafic to mafic in nature. So they're not komatiites. They can't flow far from their eruptive source. We're probably sitting on close to their volcanic conduit. So what does this tell us about setting? Well, we've got a mantle tapping setting because we're emplacing ultramafic units. We're in a subvolcanic basin, a small isolated volcanic basin with volcanic and sedimentary products in it that's potentially shallowing. And you don't just have to believe me for the actual potential for this to be mantle tapping. This is Lucy Mathieu's figure that is her interpretation of the seismic and magnetotelluric section throughout Chibougamau. And in red here, I've just highlighted the outline of the complex through the crust. And you can see directly underneath it a large section that Lucy has mapped as potentially being intrusive in nature. And that's because this is a seismic washout zone. This is a seismically quiet zone where we don't have as many reflectors. So are there any analogs for this? Well, what are the key features? We had abundant dikes and sills recording inflation. We had a central synvolcanic subbasin that tapped the mantle. And we have multiple effusive pulses of volcanism. So there are a couple good examples. The reality, unfortunately, is this kind of looks like a mixture of all of the spreading centers in the Lao. It has characteristics of all of them and doesn't perfectly match any one. But there are two pretty good analogs here, the Rochambeau rifts and the Northwest Lao spreading center that occur immediately adjacent to one another. The Rochambeau rift shows direct evidence for mantle input in the chemistry of the volcanic rocks. And note here, it's maybe hard to see, but there's a whole series on this orange rift here of purple volcanoes. It looks like it's got a fungal infection. It's just littered with volcanoes. So it's not just one eruptive site, it's numerous volcanic centers, and there's central caldera complexes here that could be analogs for a subvolcanic basin. The Northwest Lao has seen a huge pulse of volcanism directly on the rift, but also adjacent to the rift in a series of structures. And that's the same with the Rochambeau. We've got leaky plates here, areas where magma is not just coming up directly through the center of the rift, but erupting all around it as well. So let's take a look at Kivalon. Kivalon's also really interesting. It's located to the southwest of Chibougamau. You can see it in this map here, the outline of the complex. And as I mentioned before, it looks like a multi-part complex with distinct areas rather than one large composite volcanic unit. It's located directly on, again, one of these thinned areas of crust, but now we're on the northeastern structure. So this isn't one of the east-west structures that's fairly well constrained. This is on some strange northeast thing that we're really not sure about. But critically, there are VMS here. Okay, there's still VMS in this assemblage. It's still extensional in nature. And the volcanism here is Wachagabu and Roy group, and there are three main cycles in the complex itself that span over about 23 million years. So again, a long time frame of evolution. The key features here are a lack of aphanitic intrusions. Unlike Chibougamau, which is littered with dikes and sills, in Kivalon, fine-grained and aphanitic mafic intrusions are much less common, and now we see medium-grained gabbro bodies that vary in size. You can see some of the larger of these in the northern portion here, but there's actually quite a few small ones that are too small to show up on this scale of mapping. We also have a clear progression of ages from older material in the north to younger material in the southwest. And this is along the Wedding-Lamarck fault zone, which is a large fault zone that runs northeast here. And you can see it's bounding the one side of the complex. So we've got discrete volcanic centers. And critically, we don't have much synvolcanic sedimentary material here. That's pretty common throughout the Abitibi, but it's hard to explain a kind of basin or some sort of rift setting if you don't have any sediments filling it in. But we still have VMS. We're still in extension. So there are some potential analogs for this, but they're not exactly the rifts themselves. A good example might be Peggy Ridge, which is a leaky transform. That's represented in this purple here on this map, and you can actually see all of these features, by the way, in the Lao on that map that's on the ground there. So you can take a look at the surrounding area. Again, Peggy Ridge is covered with tiny volcanoes. This is a transform connecting two ridge segments where lavas have actually erupted out, forming a large flow field. But critically, this was likely not supplied like a rift with relatively continuous magmatism and volcanism. It's probably instead pulsed volcanism. And we can see some evidence for that in the scattering of volcanoes all dotting across it. And you can think that conceptually, those would not be filled with dikes, but rather with synvolcanic stalks like small gabbro units, which is exactly what we see in Kivalon. There's also a topographic high here, so there's no subbasin. This is a topographic high, it's a ridge. The next example that we potentially have here are the ridges and knolls segment. This is a volcanic flow field that develops outboard of a propagating rift. You can see here, this little orange tip here is the edge of the Phonolai rift. It's rifting in towards the arc here. You can see the island of Phonolai and a series of light purple volcanoes that are arc volcanoes. But then you can also see a series of more pink, kind of magenta colored volcanoes that are erupting ahead of the Phonolai rift here and have chemistry similar to it. So this is magma injecting ahead of the front of the rift zone and in placing and forming volcanoes here. And again, it's not continuous magma input, it's discrete pulses, and so potentially a better analog for Kivalon. So that's a lot of arm waving, but we certainly have made some steps now. If I want you to take anything away, it's these four main points here, and that's that, first of all, we can still apply this concept. We just have to think about it in terms of time, and we have to refine it using the new geochronology. The second point is that the CVCs, the Abitibi central volcanic complexes, are at the same scale as modern seafloor features. Not generally individual volcanoes, but larger features made of multiple volcanic edifices. And there are distinct types of these central volcanic complexes. They differ in morphology, in age, in VMS association, so there are distinctions we can make between them. And finally, there are comparative analogs on the seafloor. They're not perfect, but we can find features that are similar to what we're seeing in the Archean, in the Abitibi. That's it for me, thanks.